So I found this very interesting geometry problem. It's taken from SASMO, which is a competition, math competition for middle high schoolers in Singapore. So let's see how this gets tackled. Okay, so what do we have here? We have a right triangle, ABC, such that BC is equal to 8 and that AB is equal to 15, and we have a point D such that DB is equal to 6, and that this is a perpendicular. This is perpendicular, and so we're told to find the length of B correct to the nearest integer. Okay, so let's go ahead and draw the line BE, and also I'm going to draw the diagonal DC as well. And the next thing I'm going to do is I want to try and find some values of some lines, right? So the first thing I want to do is find AC. So AC, by the Pythagorean theorem, is just 15 squared plus 8 squared, which is 17. So I get 17. And since DB is 6 and AB is 15, that means AD must be 9. And then, finally, DBC is a right angle triangle, and it's also a 6, 8, 10 triangle, so this value is 10. All right, cool. We found some nice values. Now observe, okay, and this is gonna play a really huge part in our solution. We're going to observe that since DEA is right angle, this means that DEC is also a right angle, and thus we have that opposite sides are opposite angles add up to 180. So what does this mean for us? This means that the quadrilateral DEBC must be a cyclic quadrilateral. So what does it mean when a quadrilateral is cyclic? And for those that are wondering, this is the quadrilateral I'm talking about. A quadrilateral that is cyclic just means that it is a quadrilateral that is inscribed inside a circle. Okay, it can be inscribed in such a way that the vertices of the quadrilateral all lie on the circumference of the circle. Okay, so why is this so helpful? Why is realizing that this quadrilateral is a cyclic quadrilateral so helpful? Because we can now use a theorem called ptolemy's theorem. So what is this theorem? So the theorem states that for a cyclic quadrilateral, the product of its diagonals must equal to the sum of the product of the pairs of opposite sides. So that might sound a little confusing. It's probably because I haven't worded it very well, but let's take this as an example. So this theorem states that the product of the diagonals, so in this case our diagonals are DC and EB, so we have that DC times EB is equal to the sum of the product of each pair of opposite sides. So one pair of opposite sides is DE and BC, so this will be equal to DE times BC plus the product of the other pair of opposite sides, which is EC times DB. Okay, we know that DC is equal to 10, and we know that BC is equal to 8, and we know that DB is equal to 6. So all that's left to find EB is DE and EC. So that's going to be our goal. So how do we do that? Well, let's draw a simplified version of our diagram. This is just to show an important result, which is that if we call this angle alpha, this must be also 90 minus alpha. And so here must also be 90 minus alpha. This means that this triangle in red has the same interior angles as the triangle in blue. So this means that these two triangles are similar. So bringing it to our case here, we have that triangle ADE, which is this triangle here, must be similar to triangle ACB. I'm just making sure that the vertices all correspond to each other. So A corresponds to, well, A, D corresponds to C, and E corresponds to B, because these are where the right angles are. Okay, so now since we know that these triangles are similar, I can use the fact that the sides are proportional. So let's write down all the available ratios we're given, which is AD over AC is equal to AE over AB, which is equal to DE over CB. Notice that we don't have an EC, we have a DE, but EC can just be found because EC is just going to be equal to AC minus AE, which is 17 minus AE. Okay? Let's go ahead and find DE first. So AD, as I know, is 9, and AC is 17. So I'll just use this constant factor whenever I'm going to try to solve for a side. So D over CB is then equal to 9 over 17. And CB is equal to 8. So if I substitute that in and I solve for DE, I get DE is equal to 9 times 8, which is 72 over 17. Okay, great. Then I'll use the same ratio, 9 over 17, and set that equal to AE over AB. And AB here is 15. So this means that AE is just going to be equal to 15 times 9, which is 135 over 17. And so EC is equal to 17 minus 135 over 17. And so that's equal to 289 minus 135 over 17. And this simplifies down to 154 over 17. Okay, great. So now we're basically done. All we have to do now is substitute this into our formula. So 10EB is equal to 8 times 72 over 17 plus 6 times 154 over 17. And you just work this out. So you'll get 576 over 17 plus 6 times 154, which is 924 over 17. And then you add the fractions together to give us 1500 over 17 is 10EB. So EB will be equal to 150 divided by 17. And so all the calculations that I've done so far right now are that tedious to do without a calculator, because this competition doesn't allow calculators, as with any normal math Olympiad. But since we have to round off our answer to the nearest integer, you could use the method of just long division. So that's what I'm going to be doing. So 17, the most I can get out of that is just going to be 8. So we have 8. So 8 times 17 is 136. And then we have 114. So this is going to be 8 point something. So EB is equal to 8 plus some fraction. But since this is 140, and notice here that since 8 plus some fraction, so now since we have to round off our answer to the nearest integer, we have to do one more calculation to ensure that the decimal point here is greater than 5 or less than 5. And so doing a quick check shows this to be true. This is 8.8 something something. So EB is equal to 8.8 something, which rounded to the nearest integer will give 9. So the answer to this problem is EB is equal to 9 rounded off to the nearest integer. Okay, cool. Very nice problem. And even though there is no circle in this problem, we have a problem that is solved using a theorem coming from or related to circles.